gozaimasu. It's wonderful to be here. Really enjoyed coming to Japan, Tokyo, and being able to tell you a little bit more about what we're doing in the automotive industry. NVIDIA actually has been working with car makers for over 15 years. Virtually every single car on the market today was created using an NVIDIA GPU. The designers, in their early concepts, are using computer graphics, NVIDIA-powered workstations for styling and design. The engineers, as you saw from a CAD perspective, from a manufacturing perspective, they relied very heavily on visualization to be able to lay out all the thousands of components of the vehicle, to lay out the factory floors, and to model all this, again, using computer graphics and our GPU. Simulation, GPU compute is being used to do all types of work that usually would take days, weeks, or months and require millions of dollars. It can now be done virtually. So virtual crash test simulations, virtual wind tunnel simulations, virtual traction control studies can all be done interactively and iteratively to create better cars. We're also now moving GPUs, as you saw, into the cloud, but enabling the marketing and sales of cars as well. GPUs are able to do custom car configurators that can run on your tablet being connected to the cloud, or do virtual showrooms, as Audi is doing with their Audi cities around the world. Again, a virtual showroom that lets you design and customize your car. A lot of advanced technology, as you see, is being used in the design, manufacturing, production, and selling of cars. But now we're really excited to be able to take this technology and actually bring it into the vehicle itself. So NVIDIA, as you know, is well known as a computer company for creating a wide range of different types of products, from phones and tablets at the low end to laptops and desktop computers to servers and the cloud. High-performance computing, all based on a scalable architecture now. What we're doing is leveraging elements of each of these platforms and creating a computer platform for the car itself. So the Tegra processor, as you know, is a mobile computer, and now it's actually a mobile supercomputer. What we've done now is built an automotive-grade module that's the Tegra Visual Computing Module. This is what's going into cars. Essentially, this is a computer that runs an operating system. It can run Android, it can run Windows, it can run QNX, and Genevian open source code for automotive applications. This computer then has a lot of software that NVIDIA creates as well as our automotive partners work on together. But the benefit of this module is that much like your PC that you can upgrade over many years, this module is something that can easily be updated in the vehicle. The next video will show you what we've done working with Audi. This is their MID system, or their modular infotainment platform. What you can see inside is that Tegra visual computing module. This enables Audi and other customers we're working with, be it BMW, Tesla, Motors, and others, to create these systems that have a lifespan that can be extended through software updates, but also potentially by updating the hardware. In addition, since the automotive industry tracks its life cycles much longer time frame than consumer electronics, this strategy gives automakers the ability to more rapidly increase the frequency with which they update their technology. Essentially, each model year, Audi is able to introduce a new technology platform that has greater and greater capabilities. The car you saw out in front, the Audi S3, features this new system, an advanced infotainment system. If we go back to the slides, now we can see sort of the progression, in this case, what Audi is doing in terms of applying multiple generations of Tegra. The infotainment system was the first step, but now as we develop more capable processors, advanced SoCs in our Tegra line, it's being leveraged for more and more computing inside the vehicle. The TT is the new sports car from Audi coming out next year that will feature an all-digital instrument cluster. This will be powered by Tegra 3. They've also introduced a very complex and sophisticated rear seat entertainment system that will be based on Tegra 4. This will be the world's first automotive-grade tablet designed to dock in the vehicle, communicate with the vehicle, but also be able to take it out and use it as a normal tablet. And then the Tegra K1, as was announced at CES, will be used by Audi in their self-driving and piloted vehicle. Again, a lot of different applications, all based on the same Tegra architecture family. As we go back and look at now the state of the art in terms of graphics inside the car, NVIDIA is uniquely positioned to bring all the wonderful graphics research that we've done across all the different industries and types of things we'll hear about later today, and actually concentrate it and bring it into the vehicle to give the drivers and passengers a much better experience than they've ever had before. On one side, you'll see the virtual cockpit, the instrument cluster from the TT, which again is fully dynamic, can be personalized, customized as the driver wants to see things, but also changes for a context-aware situation. When you don't need a big speedometer, or you don't need the tachometer, those can shrink down and display navigation, for example. On the right side is the Tesla Model S. It in fact has two of the Tegra visual computing modules, one driving an all-digital instrument cluster, and the other driving a 17-inch touchscreen. Tesla has done something that no other car company has done. They essentially removed all the buttons, switches, and knobs and replaced it with a touchscreen that again enables the driver and the passengers to access a lot of different information and customize their vehicle experience. In addition, being a connected car, this system can be updated over the air, much like your phone or tablet. So we're seeing the automotive industry, along with NVIDIA as a technology partner, really able to mirror trends in the consumer electronics space. From a graphics perspective, though, what we want to do is really leverage so much of the wonderful research and development we've done, along with you, to bring these capabilities inside the vehicle itself. Recently, we introduced a technology called the material definition language. And what this is a very advanced way of rendering. Not just doing basic OpenGL, but instead using the compute horsepower of our GPU to actually simulate how light behaves in the real world. Many different types of materials are comprising objects that we design, build, and buy today. What we wanted to be able to do was render how these different types of materials look. On the left side, you can see an example of how car paint is actually created. It's not just a single application of paint, but actually many layers. And so what we do is we render a base layer and how light would behave when it interacts that base layer. And other coatings, there might be metallic flakes, there might be a gloss coat or two. And so we're actually simulating how photons bounce around in the atmosphere, how they react to the actual materials. And as a result, on the right side, you can see how we can render a whole range of different materials. Now, this is something that goes on all the time in the worlds of visual effects for movies, or even the beautiful renderings of cars that we do when we're trying to create a photorealistic picture. What we want to do now, and we are demonstrating, is the ability to bring that kind of visualization inside the vehicle and create a much richer experience for the driver and passengers. So this next video shows an example of a three-dimensional object, in this case an instrument cluster, being rendered with this technology, the material definition language. And here I've rotated to show you that it's actually a three-dimensional object. We can do very high resolution renderings, high frame rates, so you get very smooth animation of the needles. And then we can actually change the kinds of materials that are inside that vehicle. Render something that's chrome, maybe, or titanium, or carbon fiber. If we switch to the next video, it'll show a clip of a user interface that potentially you could use on your phone or tablet to actually customize your own car. And here you can select, do you want a powder-coated material? Do you want some form of metal, brushed or hammered? Do you want it to be copper? Do you want it to be platinum? The list just goes on and on. But we see the trend as people today customize their mobile devices, their phones, their tablets. the desire to be able to personalize your vehicle and have a unique look and feel will be very popular. So let's switch back to the slides now, and we'll talk about how, again, advances in supercomputing are really affecting the driving experience. Our goal is to make car rides more enjoyable, but even more important than that is to make them safer. Our technology, along with all the other sensors that are being put into vehicles, are going to reduce the number of accidents and fatalities on the road today. Now, it's quite astounding. There's over 1 million people killed worldwide every year in car crashes. In the United States, that number is about 34,000 people a year die. I was doing research, the number actually is very impressive for Japan. It's less than 5,000 people die annually, but still 5,000 people. Ironically, part of this research unveiled that every year about 14,000 people in Japan die in the bathtub. So I'm not sure what's going on in the bathtub, but maybe that's a topic for another GTC and a problem we can try to solve. But 5,000 people a year in Japan is still way too many. What we want to do is use computer vision, use what we call sensor fusion, the ability to bring a lot of data in, analyze it, and reduce the number of traffic accidents and fatalities. The types of features that we're starting to see on vehicles now based on these systems include pedestrian detection, blind spot monitoring, lane control systems, cruise control that actually adapts based on what's in front of the car. What I'd like to do is show you an example of a computer vision-based system that we've been developing along with a partner named Shanti. So let's roll the next video. And what we can see here is the output from a front-facing camera being fed into one of our Jetson development kits. And what we're doing is analyzing all the frames of video, doing computer vision, basically detecting objects, tracking those objects, and then we can calculate what is the speed of our vehicle relative to the other object, what is the distance from our vehicle to that object, where are the lane markings, what are the street signs, and we can basically then become a brain that is the co-pilot to the driver. We can actually figure out what's going on around the car and alert the driver or potentially control the vehicle to avoid a potential hazardous situation. Let's go to the next slide. There's a huge amount of computation going on here. Many layers, and this is part of the VisionWorks toolkit. Again, CUDA is enabling computer vision to operate in real time here. Essentially, what we're doing is 3D graphics in reverse. We're taking data, in this case maybe video, that's two-dimensional data coming in. And we have successive frames. So we can run different algorithms, like structure from motion, for example, where we're able to detect what's moving and also get a sense of depth. So we can detect features in these scenes. We can then track them using our machine learning capabilities, understand what those objects are, and then actually build a three-dimensional scene of what these sensors are taking in. So the next video shows something that we've demonstrated with Audi. And in this case here, what you're seeing is a side-facing camera. As the car drives by, it's looking for a place to park. What the camera senses, again, is just video. What the GPU is then doing is interpreting that video, creating a sense of notion of what is near, what is far, what is an object, what is not, and building these 3D fences. Then when it detects an opening, it's able to then sense that and will signal a place to park has been found. Again, this is all great stuff. It's all working in the labs. We have Nissan announcing autonomous vehicles. We have BMW, Audi, and many others really working on this. What we're really excited to be able to discuss with you today, though, is something that Audi showcased initially at CES, demonstrated at the last GTC that we hosted in San Jose, and now we'll be going into series production. This is something that the code name is ZFAS, and what it is, again, is a piloted driving system. In the past, it required 4 large computers in the trunk to be able to process all the sensor data on the coming into the vehicle. What the system would do, though, is be able to detect other vehicles, maybe on the highway, when there's a traffic jam. The driver can turn on traffic jam assist. The car will then stay in the lane and maintain a safe distance to the car in front. So essentially, it's driving itself. The driver can take their hands off the wheels, take their feet off the pedals, and not have to worry. Then when the traffic dissipates, the system turns control back over to the driver, and they take over. Another mode, and it's very exciting of how this will be implemented, is in self-parking, where the driver can actually get out of the car, press a button on the key fob, and the car will go into a parking lot, find an open spot, and park itself. And then when you're done, say you're leaving a conference, you press a button on the key fob, and the car is going to come out of the parking lot and pick you up where you left off. Now, the image on the left isn't practical, but with Tegra K1 now, Audi is going to market with a system that will fit in the trunk of the vehicle, that will again enable this traffic jam assist, self-driving, as well as the self-parking. So there's a lot of great advancements going on today. The GPU is at the forefront of automotive. Sorry, getting it. Thanks. Oh, looks like my car's out front. Have to go. Thank you very much, and I'd like to please welcome back David Kirk.